the first thing we can do is find when the slope equals 0. And we can tell that the slope equals 0 when y equals -1. Because when the slope is equal to 0, the numerator is equal to 0. And when the numerator is equal to 0, y is equal to -1. So for the line y equals -1, all the points at that line have a slope of 0, which is indicated by these purple lines. Next, we can find when the slope is undefined, and we can tell that the slope is undefined when x equals 0, because the restriction that they gave us was that x cannot equal 0. Because when x is equal to 0, the denominator is equal to 0, which makes this equation undefined. Thus, along the y-axis, or when x is equal to 0, we do not mark anything, because the slope is undefined. For all the other points, we can plug in their x and y values back into the differential equation, which is outlined in red. So for example, for the point 2, 0, x is equal to 2 and y is equal to 0. Plugging these two values back into the differential equation, we get 1/2. And we can do these for all the other points that do not have a slope of 0 or a slope that is undefined. Looking at the grading outlines that was provided by the AP exam key, we can tell that there is a total of 2 points given for this problem. And to receive these 2 points, you had to have the sign of the slope at each point and relative steepness of slope lines in rows and columns. In order to find the particular solution, we must first find the general solution. The first step to finding the general solution is to separate the variables of the original differential equation. This is the original differential equation. To move 1 plus y over to where dy is on the other side, we divide the whole equation by 1 plus y. To move dx over to where x is on the other side, we multiply the whole equation by dx. Now we will integrate the resulting differential equation after the separation of variables. The resulting equation is ln of absolute value of 1 plus y, which is the antiderivative of dy over 1 plus y, is equal to ln of absolute value of x, which is the antiderivative of dx over x, plus c. Do not forget the plus c, because that is what makes it a general solution. The next step is to get rid of the natural log. Getting rid of the natural log allows us to solve for y a lot easier. To get rid of the natural log, we take e to the power of both sides. So e to the power of ln of the absolute value of 1 plus y is equal to e to the power of ln of the absolute value of x plus c. To simplify, this results in the absolute value of 1 plus y is equal to e to the power of ln of the absolute value of x times e to the c. The right side portion of the resulting equation results from the rule of exponentiation. Because when two exponents are multiplied together with the same base, in this case e, the powers can be added together. The next and fourth step is to find the constant of integration, or to substitute e to the c with k. Since c is a constant, e to the c will also be a constant, and we can denote this constant as k. So we have the absolute value of 1 plus y is equal to k times e to the power of ln of the absolute value of x. E to the power of anything can't be negative, so we can remove the absolute value signs off of 1 plus y. However, even if we were to keep the absolute value signs so that the equation would become 1 plus y is equal to positive or negative k times e to the power of ln of the absolute value of x, the resulting k would still be the same as the k from the previous logic. Here's why. We're going to take this equation, underlined in black, and plug the initial conditions of x equals -1 and y equals 1 given from the problem into the equation. As a result, we get 2 equals plus or minus k, or k equals plus or minus 2. To determine whether k is positive 2 or negative 2, we can make equations using these two differing values. So for k equals 2, we have the equation 1 plus y equals 2 times e to the power of ln of the absolute value of x. All we did was plug positive 2 back into k in the original equation. We find that 2 equals 2, which is what we want. For k equals negative 2, we have the equation 1 plus y equals negative 2 times e to the power of ln of the absolute value of x. However, in this case, we get 2 equals to negative 2, which these two values do not equal. Thus, we know that the value of k is positive 2 instead of negative 2. After plugging in the initial condition, we can now solve for y. Since we know that k is equal to positive 2, we have the equation 1 plus y is equal to 2 times e to the power of ln of the absolute value of x. E to the power of ln of the absolute value of x is the same thing as the absolute value of x. So now we have the equation 1 plus y is equal to 2 times the absolute value of x. To isolate y, or to solve for y, we get y is equal to 2 times the absolute value of x minus 1. This is the particular solution to the differential equation. So now that we have our particular solution, we can now solve for the domain of that particular solution. If we remove the absolute value signs off of the original particular solution, we get the equation y is equal to 2 times x minus 1. Plugging in the initial condition into that equation, we get that 1 does not equal to negative 3. But if we add a negative sign in front of 2x, we get that 1 is equal to 1, which is what we want. So now we can say that y is equal to 2 times the absolute value of x minus 1 is the same as y is equal to negative 2x minus 1. But to find the domain, we take the derivative of both these equations and set them equal to each other. We find that x has to be less than 0 or a negative value. To check this domain, we take both these equations again and plug in an x value that fits the domain, so any negative number. For this case, I'll be using negative 1. We find that when we plug x is equal to negative 1 into both these differing equations, we get the same y values for both these results, 1. So now we can say that our domain does work for both these equations, and this domain is the correct domain for the particular solution. This is the grading guideline for this part of the problem. There's a total of 7 points given to this problem, the majority of which is given to finding the particular solution. 1 point is for separation of variables, 2 points are for the antiderivatives, 1 point is for the constant of integration, 1 point is for the utilization of the initial condition, and the last point is for solving for y. And the steps listed right here are exactly the steps that we did in the problem. The last point goes to finding the domain. So the important part to remember is to not forget to find the domain and to always get the particular solution even if you can't find the domain, because the majority of the 7 points, 6 points, goes to the particular solution. These are some similar problems. Note that all of these problems are either number 5 or number 6, meaning that no calculators are allowed on any of these problems. I'll link the problems and their video lessons in the description box below.